Good morning, friends. Today we will discuss about the V and inverted V curves of a synchronous motor. So, what do you mean by V curve and what do you mean by inverted V curve? So, V curve. So, it is the characteristics or a curve between armature current versus the field current. Armature current IA as well as field current IF. Okay. So, how to draw this V curve? Okay. Suppose for initially you start the synchronous motor, okay, by external starting methods. After that, so you need to provide the field current. Once you provide the field current to the poles of the synchronous motor, so that is called as excitation. So the synchronous motor goes on increasing its speed and it will catches the synchronism, okay, or it will catches the synchronous speed. So at that moment, so if it goes on increasing the field current, so the armature current is going to be decreases at some point. For example, it is a 8 ampere is the full load current of the motor, so up to 2 ampere or 2.5 ampere, so your curve is going to be reduced, that is the armature current is going to be reduced at the initial stages. After that, if it goes on again increasing the field current, suddenly the armature current is going to be increases. Okay, so this is the curve between these two. So now for no load condition, so initially don't put any load on the synchronous motor, so that is either braking load or some any external load. Okay, so you keep it no load condition, so only you change the field current, so you will get the curve like this. This is for no load curve. After that, you put some load. Okay, so suppose it is a for a half load or quarter load, 30% load. So okay, so that is second one is for half load. Okay, if it is a motor having a 8 ampere, so you put 4 ampere, that is called as a half load. Okay, so at that condition again you repeat the procedure for the field current, that is IF, you goes on increasing, so then your armature current is goes on decreasing from 4 ampere to again it will be reduced to 2 ampere, again it is going to be increases to the 4 ampere. So this is in the shape of V, hence it is called as a V curve. So there are 3 points here, point A and point B and point C. For the armature current, it will falls from point A to point B, then it will be rises from point B to point C. Okay, for full load current, suppose it is a 8 ampere machine, so apply full load by applying a brake. Okay, so then you apply the field current, so then you will get the curve like this. Okay, so again you will divide these things in two divisions. So for unity power factor and lagging power factor and the leading power factor, draw a dotted line in between that. So in the lagging case, so that is called as under excitation. Under excitation means, so we have less field current, so less field current, that is called as under excitation below this dotted line. So after this dotted line, we can call it as this is over excitation. So if you increase the field current, that is called as excitation is over. Okay, so hence when over excitation, always it is called as a leading power factor. Okay, and in under excitation, always we will get a lagging power factor. So in between lagging and leading, the middle point, so that is called as the unity power factor. Okay, so this is called as the V curve. So similarly, inverted V curves that can be drawn uh, the same thing, but instead of armature current, so we'll draw the power factor versus field current. Okay, so while doing this experiment, according to the while taking the same armature current, so along with that you take the power factor reading also. Okay, so the power factor reading, that is inversely proportional to this previous characteristics. So what happened, the power factor versus the field current, if you goes on increasing the field current, so power factor is going to be increases. Okay, then again if you increase after the unity power factor dotted line, that is called as over excited line, then power factor is goes on decreasing. Okay, so this is called as power factor versus, that is the cos pi versus the field current. So if you put a cos pi value is 1, that is called as a unity power factor. So this will called as a unity power factor line. Okay, and similarly in previous case the lagging and leading power factor, that is shown in the below the dotted line, that is the beginning of the dotted line, so that is called as a lagging in nature. After the dotted line, that is called as a leading in nature. Okay, so that is in lagging, that is the under excitation, and for leading this is the over excitation. So this curve is termed as inverted V curve. So this is about V curves and inverted V curve. So in three cases, that is the unity power factor, lagging power factor, and leading power factor, the vector diagrams are shown here. So the V is taken as reference, and EB is the back EMF. Okay, and the angle between the V and EB, that is called as load angle, that is called as delta, and IA is the armature current. So initially this is the armature current for lagging power factor. So IA is lagging behind the supply voltage by an angle pi. Okay, so then IA axis that can be drawn. This is the, if you join these two, so this will use the V. Okay, this is for lagging power factor. Similarly for unity power factor, this IA, it is in phase with the V, so the pi will become 0 because cos pi is equal to 1. So if pi is 0 means cos pi is 1. So IA and V both are on the same line. So and you draw the perpendicular, that is IA axis along with this. So then we'll join these two. This will give the back EMF, that is EB. The angle between V and EB is called as delta, and this is called as IA cos pi distance. So this here also, this is the IA cos pi distance. And for leading power factor, so IA, so that is leads the supply voltage V, okay, by an angle pi. This is the third case. Okay, so in this case pi is 0, in this case pi is negative, in this case pi is positive. So this will give the power factor is leading in nature. So that's IA axis, you draw this IA axis in opposite direction, and so you join these two, this will give the back EMF line, that is the EB line. Okay, so this is about the V curves and inverted V curve. So it can be easily noted that from this curve, an increase in the shaft load requires an increase in the field excitation in order to maintain the power factor unity. So this sentence you have to keep in mind. Okay. So next, so another point is, and the points A, B, C on the upper curve corresponds to the operating condition of the phasor diagram. So note that the for P is equal to 0, suppose the power is 0, the lagging power factor, it will be operating in the lagging power factor operation, electrically equivalent as an inductor. So synchronous motor, if it is running under lagging power factor, so at the P becomes 0, so it is acts as an inductor. If it is a leading power factor operation, it is acts as a capacitor. Okay, so hence it is used as a synchronous condenser operation while in the capacitor mode. So that is the leading power factor mode. So hence over-excited induction, over-excited synchronous motor, it is operated as a synchronous condenser. Okay, so that is the one of the major application of synchronous motor. Okay, so what is synchronous condenser? So this is a synchronous condenser. Suppose this synchronous motor, over-excited synchronous motor, acts as a synchronous condenser. It is running under leading power factor. So that can be put across, that is connected across or shunt with the any industrial load like a induction motor. So the induction motor is lagging in nature. Always the power factor is lagging in induction motor, that can be compensated. The power factor can be compensated by means of the synchronous condenser. Okay, so that is improvement in the power factor that can be achieved by means of synchronous condenser. Okay, so in this diagram figure A, So it will show the three-phase induction motor load that is connected in some industries. So the AC supply is given to the three-phase induction motor, it will operate. So looking at the phasor diagram, this is supply voltage is V. So the induction motor operating in the lagging power factor. So that is the lagging current, that is IL, that is lagging behind the supply voltage. So by an angle pi L. Okay. So now, if you want to increase this lagging power factor, that is you have to improve the power factor correction. We need to reduce the angle between these two. So then you connect a synchronous condenser. So this is the stator part of the synchronous motor. So again you connect it parallel with this. So then the current flowing through the synchronous condenser or synchronous motor, that is represented by IM, that is in leading in nature. So it leads the supply voltage V by an angle pi M. Okay. So now there are two currents are parallel here. So one current is flowing through the induction motor, another current is flowing through the synchronous motor. The summation of these two currents is called as a total current. So in the total line power factor that can be increased. So by means of addition of these two current, so it will resultant in the current, so that will be nearer to the supply voltage. So therefore the power factor, the angle between these two is again reduced. So if angle is reduced, the power factor is going to be increases. So because cos pi, if cos pi is 0, so power factor is 1. If pi is very nearer, so it is in terms of 20 degree or 30 degree. So instead of 70 degree, so we will get, so the power factor nearly zero point 0.8 or 0.995. So that is improvement in the power factor from the 0.7 lagging to the 0.9. So this can be achieved by means of synchronous condenser. So this is about synchronous condenser. The definition is the overexcited synchronous motor operates at leading power factor is called as a synchronous condenser. In large industrial plants, the load power factor will be lagging. The specially designed synchronous motor running at a zero load, taking a leading current approximately equal to 90 degree when it is connected in parallel with the inductive load. To improve the power factor is known as synchronous condenser. Comparing to the static capacitor, the power factor can be improved easily by varying in the field excitation of the motor. So by varying the field excitation, that is the IF, the field current, so we can achieve, that is the over excitation. So then the power factor can be improved of the induction motor. Phasor diagram of synchronous motor, that is shown in the figure. Okay. So next topic is hunting. So what do you mean by hunting? Okay. So a synchronous motor, suppose sudden change in the load. Okay. So it is connected to some load. Because of so many reasons, load is going to be varied. So that variable load or some variable frequency or frequency of supply frequency is pulsating. So these are some of the causes for hunting. So what happened? Cause this, a sudden change in the load of the synchronous motor may sometimes set up some oscillations in the motor. Okay, those superimposed oscillation on the normal rotation resulting in some periodic variation. So of these very low frequency in speed. So these periodic variations are produced, that is very low frequency in speed. This effect is known as hunting. Okay, it is also called as phase swinging. Okay, so what happened, the rotor is running, rotor of the synchronous motor running under some speed that can be dropped because of the variation in the load. Due to that, some oscillations are produced in the rotor. So those oscillations, superimposed oscillation, that will cause us some effects on the rotor. So this effect we can call it as hunting. Okay, occasionally the trouble in the a motor, that can be natural periodic of oscillation approximately equal to the hunting period. When the synchronous motor phase swings into the unstable region, the motor may fall out of synchronism. So what happens? So if hunting effect is increases, so it will fall out of synchronism. If it is out of synchronism, the synchronous motor does not rotate under the synchronous speed. So then motor is going to be stopped. So hence, so this is the one of the effect of the hunting. How to reduce the effect of hunting? So that can be reduced by providing the damper winding. So the damper windings are provided on the motor poles, on the pole shoes. Okay, so these damper winding, so that will nullifies those superimposed oscillations, so that can reduces the hunting. And what are the effects of hunting? So we'll discuss some effects of hunting. Due to hunting, the load angle delta will be changed. So delta is the angle between what the supply voltage and the back EMF produced. Okay, that angle. So this delta, it should not exceed 90 degree. Suppose if it is more than 90 degree, the motor fall out of synchronism. If it is out of synchronism, it is very dangerous in the nature. Okay, so if it is out of synchronism means there are connected parallel synchronous machine. If it is uh, running under unstable position, if it is instability happen, the motor it will fall into the uh, fall out of synchronism. Okay, so as delta changes for the same excitation, that is EB, the current drawn by the motor is also changes. Okay, so due to that, the current drawn by the motor, that is also the change in the nature. So it will cause us, because the same line is connected to some other appliances. Due to that change in current, so that is causing the other appliances also. The current drawn by the motor, which may cause problem, the other appliances connected in the same line. Because of this excess current will be drawn by the motor. Okay, due to hunting effect. And if oscillations are for longer period, suppose the hunting effect is happened, at that time the superimposed oscillations are produced. So if you have to nullify this oscillation within the critical period, otherwise, so if it is oscillations are longer in nature, so then the motor come out of synchronism. So there is some time before critical time, you have to neutralize those oscillation. Okay, otherwise the mechanical stresses on the rotor are severe, and current drawn by the motor is also large. So motor gets subjected to the large mechanical load and electrical stresses. So this is the some of the effects happened in the synchronous motor. Okay, and this is one of the disadvantage of motor is called as hunting. So for the remedial purpose, we require, will provide some damper winding on the pole shoes of the motor pole, that is connected in the rotor. So that will nullify the hunting effect. The tendency of hunting can be minimized by use of damper winding. Okay, so damper winding are placed in the pole phases. So already told, that is placed in the pole phases. No EMF induced in the damper bars, and no current flows in the damper winding. Okay, so these are some dummy coils we are providing here. So that is called as damper windings or damper bars. So there is no current flowing in the these winding. Whenever irregularity takes place, okay, so when it will be operated under normal condition, these damper windings are not operating. So damper windings are used for starting purpose of the synchronous machine. After that, so there is no current flowing through the damper winding. So then suppose any variations in the load, irregularity happen, the hunting effect will be occur at that time. So what happened? The irregularity takes place, the speed of the rotation. However, the polar flux moves from side to side of the poles. This movement causing the flux to move backward or forward. So at that time, the variations in the speed or load angle, so it will result in the variations in the flux movement in one pole to another pole, or one side to another side, either some backward direction or forward direction. So across the damper bar. So this tend to the damp out the superimposed oscillation. So damping means, so suppose the continuous variations in the signal. Okay, so this is called as damping, bouncing, you can call it as bouncing. After that, it has to come to the steady state, it will become the straight line. Suppose if you take a ball, so uh, you play with the ball. Okay, so you strike the ball to the wall or a ground. So what happened, the ball is continuously so varying. After some time, it will come to the rest position, so that is called as damping or some bouncing. So similarly, the oscillations also, so the continuously it will be varying, that is called as oscillation. After some time, it will come to the synchronism or equilibrium position. Okay, so this is the curve shown here. The angle between, that is the load angle with respect to the time. If you draw this, so this is called a superimposed oscillation, that is the delta angle. It is continuously varying, okay, under the unstable region. So what happens, whenever disturbance occur, these oscillations will be produced. So this is the setting time due to the damper winding, the setting time of hunting. So this is the hunting period, so without damper winding. So if you use the damper winding, we can reduce the hunting time. So the second curve, it will reaches the steady state, so within this setting time. So therefore, because of damper winding, the setting time is going to be reduced, so the motor comes to the steady state before uh, it will fall out of synchronism. So hence, these damper windings are plays important role while hunting period. Okay, so this is about hunting and as well as damper winding. And last topic is comparison of synchronous motor and induction motor. So these are some general discussion. That is the synchronous motor. So what are the common differences of synchronous motor as well as induction motor? So construction wise, the synchronous motor is complicated and induction motor, it is very simple. How means, the construction of synchronous motor, so it also involves some damper winding and some additional requirement is required for the starting period. Hence the construction is difficult, because it carries a magnetic force in the rotors and stator part having armature. And in this case of induction motor, stator is armature winding, and we can use the short circuited squirrel cage rotor or slip ring rotor. So this is easy construction in induction motor and easily available uh, induction motor. Okay, and self-starting, induction motor is self-starting. Synchronous motor is not self-starting. So as we discussed, so it has to start by means of some polymo motors and some induction motors or some DC motor or some damper winding. Okay, pony motor. So like that, so you have to use some additional equipment to start the synchronous motor. Okay, that is a disadvantage. And separate DC source is required for the motor excitation or motor poles. So we require separate DC excitation along with the AC supply. There are two different sources are required here for to start the synchronous motor. But in case of induction motor, so it is only a three-phase supply is required to rotate the induction motor. That is, rotor gets excited from the induced EMF directly. So here the rotor does not require any other DC supply in case of induction motor. And speed of the synchronous motor, N is equal to Ns. N means rotor speed is equal to synchronous speed. But in case of induction motor, always rotor speed less than the synchronous speed. Suppose synchronous speed is 1500 rpm, rotor speed is also 1500 rpm. So in this case, synchronous speed is 1500 rpm, though your rotor speed is less than this. So normally, probably it is 1440 rpm. Okay, so depending upon the slip. And speed control is not possible in case of synchronous motor. Speed control can be achieved here by various techniques, the stator resistance technique and rotor resistance technique, and some auto transformer and voltage control method and frequency control method. So we can control the speed of the induction motor. It's also some difficult. Okay, and also, as load increases, the load angle increases, keeping speed constant. at synchronous. So if you increase the load, so what happens, load angle is also going to be changed. So due to that, speed increases, keeping the speed constant at the synchronous speed. So in this case, what happens, as the load increases, the speed keeps on decreasing. In case of induction motor, that is a disadvantage. But in this case, synchronous motor, as ever the irrespective of the load, synchronous motor having constant speed. Okay, and by changing the excitation of the motor, power factor can be changed from lagging to leading. So that is one of the advantages of synchronous motor. So in case of induction motor, always it will be operate in the lagging power factor. So power factor cannot be controlled. So it cannot be improved in this case. So if you want to improve the power factor of induction motor, again you require a synchronous motor or some capacitor. Additional device is required to increase the improvement in the power factor. Okay, and eighth point, it can be used as synchronous condenser for power factor improvement. And so induction motor, it cannot be used as a synchronous condenser, and hunting effect is present. This is one of the disadvantages in synchronous motor. Hunting effect is not present, that is absent in case of induction motor. And synchronous motors are very costlier because of so much complexity in the construction and all those things, required some frequent maintenance also. But this induction motor, it is available very cheap, and especially cage motor, that is a coral cage motors are very cheap, and maintenance is also very free. Okay, so hence almost all industries are using for a lot of application for induction motor. Okay, so this completes the synchronous motor. This completes the synchronous motor chapter. So thank you very much.